pleasure to introduce Professor Emmanuel Breuillard from Cambridge University. Emmanuel has worked on very different fields, mathematics, having lasting impact on combinatorics, number theory, and group theory. He was awarded the European Mathematical Society Prize in 2012 for his deep research in asymptotic group theory. In 2013, he won the Charles-Louis de Freycinet Prize from the French Academy of Sciences. Emmanuel's career is truly international. He studied at CNRS Paris, Cambridge, and Paris Sud, Orsay, and Yale. And after that, he worked at Paris, a number of universities, Polytechnic, and Paris Sud, and University Münster in Germany. And right now, he just returned to us. So we are very glad to hear him speaking on homogeneous flows and Diophantine geometry.
All right. Thanks. Okay. Thanks very much. Thanks very much. Yeah. Yes. Yes, I'm a Frenchman in Britain. Just started to work at the University of Cambridge. Etienne mentioned this morning that Demoivre couldn't get a job in Cambridge. So obviously things have changed, and I'm much luckier than he was. I'm going to talk about some subject which connects number theory and dynamical systems and group theory at the end. So I will start a long time ago when, in the antiquity, when people tried to understand the notion of what is a real number. So one way to define a number is to look at the integers and maybe take fractions of integers. So P over Q. Yes, so if you take two integers, P and Q, then you can form a fraction P over Q. So the set of numbers of the form P over Q, where P and Q are integers, are called rational numbers, right? But now if you take another real number, which is not of this form, not of the form P and Q, P over Q, then a natural question is how well can you approximate it by fractions P over Q? Okay, so this is a very well-known and very well-studied subject called Diophantine approximation. So, so here's an example. If you take square root of 2, the Greeks knew that square root of 2 is not a rational number. And you can try to approximate it by rationals. So here is a sequence of increasingly good approximations of square root of 2 by rationals. And here is a picture of a Babylonian tablet, clay tablet from something like 4,000 years ago, which shows an even better approximation, better than this, to square root of 2. And you know that the Babylonians counted in base 60. So the numbers that you see there are the digits in the base 60 approximation of square root of 2. And so amazingly, they got, I think, 6 decimal digits right here. Okay, so it goes a long, long time ago. Yeah, square root of 2 is irrational. This is one of the proofs, the first proofs in number theory, which you can understand in before high school, or even in elementary school. So here's one possible proof. So there are many different proofs, but here's one of them. So first, if you want to show that square root of 2 is irrational, then you prove the following claim. If I take two integers p and q, then the square of an integer can never be equal to twice the square of another integer. Okay? And the reason is that if you look at the largest power of 2 dividing a square, it has to be even. Because if 2 divides p squared, then 2 divides p. And therefore, there is an even power of 2 inside p squared. Now, if you take twice a square, then the largest power of 2 must be odd. So the 2 can't be the same. Okay? And this gives a proof that square root of 2 is not rational, because if square root of 2 is p over q, then squaring, you would get 2q squared equals p squared. And this is not possible because of what we've just said. Okay? So if you think about it, then this proof actually gives a bit more. A bit more than saying that just square root of 2 is not rational. It tells you that square root of 2 cannot be too well approximated by rational numbers. Why? Because we've shown that 2q squared minus p squared is non-zero, but it's an integer. So if it's non-zero and an integer, then it has to be at least 1 in absolute value. Okay. So you get this inequality here. And from here, you look at, if you want to estimate the distance between square root of 2 and a fraction p over q, then you multiply, you do what we do in high school, right? You multiply the top and the bottom by square root of 2 plus p over q, and you get 2q squared minus p squared divided by something at the bottom, which will be positive, in fact, bigger than q. So smaller than q, smaller than q square root of 2. So you get this inequality here, 1 over 3q squared. Okay? So if you measure the rational numbers, if you measure the complexity of a rational number by the size of p or q, then you see that you can't approximate square root of 2 too well, and the lower bound is something like inverse quadratic in q, 1 over q squared. Okay? So that's one way to measure the difference, how well you can approximate a number which is not rational. And one way to do this is to introduce this number, which sometimes is called the irrationality measure of your irrational number, or sometimes called the Diophantine exponent. So we call it the Diophantine exponent of a number alpha, is the smallest power beta here of q, which has with which you can lower bound the distance between alpha and any fraction, any rational number p over q. Okay, so the larger beta is, the better you will be able to approximate alpha. Okay, and the smaller beta is, the worse you will be able to approximate alpha. So you see that square root of 2 here is quite badly approximable, because you have only beta is equal to 1 in this case. You have q squared, which means that beta is equal to 1. Okay. So there are numbers which are not rational and but still are very well approximated. For example, you take a decimal, you look at the decimal expansion of a number, and you put lots of zeros, and then eventually a 1, and then lots of zeros, and then 1, and so on. And so those numbers are called Liouville numbers. Their beta is infinity, and they're very well approximated, but they are still irrational. So one of the first theorems about this number beta is due to a German mathematician from the 19th century, Dirichlet, and he proved the following: if you have any integer capital Q, then you can find a fairly good approximation, rational approximation, p over q of alpha, with little q, how do I get out of this? Yeah, thank you. I pressed the wrong button. Sorry. God. Okay. All right. Good. Yeah. So the theorem says that if you give to yourself a certain approximation, a certain 1 over q, certain epsilon of approximation, then you will be able always to find a good approximation p over q, which is as good as this shows here, 1 over q squared. Okay. So the reason is if you divide by little q here, because capital Q is bigger than little q, then you get 1 over q squared instead of 1 over capital Q little q. Okay, so from this you see that that the Diophantine exponent of any number is at least equal to 1. Okay, so this is why square root of 2 is somehow the worst possible case. Right? You cannot approximate square root of 2. It's like the worst number possible, the worst quality of approximation. Okay, so for example, pi, the number pi is known to have a finite exponent. So when the exponent is finite, you call this number Diophantine. And pi is known to be Diophantine, to have finite exponent beta, but it's not known whether this exponent is 1 or not. Okay, so there are upper bounds, known upper bounds on beta, but it's not known whether it's as bad as square root of 2 or not. But what is known is that if you pick a number at random, a real number at random in 0, 1, according to Lebesgue measure, just pick a number at random, then this exponent will be 1. Okay, so it will be as bad as square root of 2. Okay, so all right, so the behavior of a random number is the same as the behavior of the worst possible number, and is the same as the behavior of numbers like square root of 2. The next class of numbers I'd like to discuss is called the algebraic numbers. So square root of 2 is a particular number because it's a root of a polynomial with integer coefficients, like 2 alpha squared minus 1, right? So more generally, if you take an arbitrary polynomial equation with integer coefficients, like a0 plus a1 alpha plus a2 alpha squared and so on, then the roots of these polynomials, the solutions of these polynomial equations are called algebraic numbers. Okay? And so, for example, pi famously is not an algebraic number. Okay? So this is one of the crowning achievements of 19th century mathematics. It was put an end to the famous problem of squaring the circle, drawing a square with a ruler and compass that would have the same area as a given circle. So, right. So now the question is, can we understand the Diophantine exponent of an algebraic number? And, well, Liouville in the 19th century was the first to observe that, in fact, every algebraic number has a finite Diophantine exponent. And his proof is roughly similar to the one I've given to you for square root of 2. So you can essentially show that using conjugates of your number, you have a product which is an integer, has to be bigger than 1, and then you can't approximate your number too well. That's one way to prove it. So in particular, this beta is finite, and however, the proof the proof of Liouville gives a beta which depends on the degree, on the d here, on the minimal d, which for which alpha satisfies an equation of degree d. And now comes the final answer to this question of determining beta for algebraic numbers. So this is Ross' theorem, So Ross theorem was proven in the early 50s by Klaus Roth, who's a German-British mathematician. And he established that beta is equal to 1 for every algebraic number. So namely, so this means that, so if you translate what it means that for every epsilon, you can find a constant C epsilon such that for every rational number P over Q, then the distance from P over Q to alpha is bounded below by constant divided by Q to the 2 plus epsilon. Okay, so you can't really approach 2, but almost. Okay. So yeah, so this shows that beta of alpha is equal to 1 if alpha is algebraic. So the proof was, so actually Roth won the Fields Medal for this proof because it was a very technically involved argument which built on a method introduced by Tu and by Siegel and worked on by also Freeman Dyson, who was a young fellow at Trinity College just after the war, before he became a famous physicist. He proved he proved an improvement on the beta of alpha. But these bounds, before Roth, these bounds were depending on the degree of alpha. Okay, so Roth was the first to show that in fact this beta does not depend on the degree of alpha. For every algebraic number, the beta of alpha is equal to 1, which means that it's the same as a random number. Okay, so the Diophantine exponent of a random number, a real number, is the worst possible Diophantine exponent, and it's the same as the Diophantine exponent of any algebraic number. Okay, good. One interesting feature of the proof, which is still unresolved nowadays, is the fact that this constant C epsilon is ineffective. So this means that there is no explicit bound on the constant which could be derived from the proof from the input, and the input date from the data for the input data. And the input data is this number alpha, and maybe the polynomial which defines alpha, with who's such that alpha is the root of that polynomial. So it's ineffective, and there's no way around it. At least we mathematicians haven't been able up to today to find a proof that would give an estimate on this C alpha. But if such a proof existed, it would have a lot of applications in finding explicit solutions to Diophantine equations, to equations with integer coefficients. So finding integer solutions to polynomial equations. So however, although the C epsilon is not effective, then if you're given a given alpha, a C and an epsilon, then you can find a good estimate on the number of rational approximations. So so maybe alpha is not well approximated by rationals, but maybe there are only 2 or only 3 very, very good approximations. Okay, so this theorem says that it can't be too well approximated, but you can find a bound on the number of possible exceptional approximations to alpha. Okay, and this bound is effective. So about 20, 30 years later, Wolfgang Schmidt, here that you see here, came up with a vast generalization of Roth's theorem, and he showed the following very important theorem in the 70s. Suppose you have L1, Ln, linearly independent linear forms in n variables with algebraic coefficients. Okay, then for every epsilon, you can find a constant C epsilon such that if you look at this equation, this inequality, if you look at this inequality, then it always holds for every q. Q is a tuple of integers. except when Q belongs to a finite set of smaller subspaces. So think of it as being in the space Rn. Inside Rn, you have Zn. And you look for solutions I mean, you take the product of these linear forms. And this product is never too close to 0, explicitly in this form. And the exceptions to this inequality all contain infinitely many proper subspaces. So it's a generalization of Ross theorem. And in fact, if you take n equals 2, what you get is just Ross theorem. It's just a Ross theorem is just a product. You have Q times Q alpha minus P, so it's a product of two linear forms. Okay, one is just Q, the other one is Q alpha minus P. They have coefficients, they have algebraic coefficients. So if you apply this theorem to n equals 2, you recover a Ross theorem. The two are equivalent. The number of exceptional subspaces can be explicitly bounded. But again, this constant C epsilon here is ineffective. Okay? And the proof of Schmidt uses the same general idea of Roth. So but it's much more involved, but it's similar ideas. So here's a consequence of the Schmidt subspace theorem. So instead of trying to minimize Q alpha minus P, so trying to find an approximation of alpha by P over Q, you may want to find not a linear form, but a polynomial in alpha that would make alpha small. So you may try to minimize P of alpha, where P is a polynomial with integer coefficients. Okay? And you want to say that this is not, because if alpha is algebraic, you want to say that this is, of course, if alpha is algebraic, then you could take P to be the minimal polynomial defining, such that alpha is a root of that polynomial. Okay? And then you would get that P of alpha is 0. Okay? But now suppose that the degree of alpha is much bigger than the degree of P. Then P of alpha cannot be 0. And you want to say, well, if it cannot be 0, then it has to be bounded away from 0 in an explicit way. And so from the Schmidt subspace theorem that I've just stated, you immediately get the following lower bound. The value of alpha, of any polynomial evaluated at alpha, any polynomial with integer coefficients, and degree smaller than alpha, is bounded away from 0 by this explicit quantity here. Okay, so it's a corollary of the previous theorem. So now, Kurzmaler, who you can see a picture here, and was also a prominent number theorist in the first half of the 20th century, conjectured the following thing. They conjecture that, similarly, if you take a random alpha, then again, you have a lower bound of the similar form. So if you take a number alpha at random, a real number at random, then you can't really, so typically it won't be an algebraic number because there are only countably many algebraic numbers, and that has measure 0. So if you take P of alpha, where P has integer coefficients, P of alpha, then it can't be too small. And he conjectured that the right lower bound is the same as the one that we saw before for algebraic numbers. So and so this conjecture was solved by a Russian mathematician Sprinjuk in the 1970s, using essentially, using interesting, but essentially classical number theory. But just about 20 years ago, Kleinbach and Margulis two other Russian mathematicians, came up with a completely different proof. And that's what I want to tell you today. So they came up with a different proof based on a completely different idea, based on dynamical systems. The idea is you can look at, I skipped 2 slides, I'll come back. There is a certain space which I write like this. And this space is the space, very concrete space, a space of lattices in RD of covolume 1. So think of Z to the D inside RD. Z to the D is a lattice in RD. So it's like a grid, right? And it has covolume 1, okay? Now you can deform this lattice by affine transformations, and you get another lattice. And the set of all possible deformations is what I call the set of lattices in RD. It's a very nice set because it's a homogeneous set. So you can look at the group of affine transformations, SLDR, and it acts on that space in a homogeneous way, in a transitive way. You can get from any point to any other point by applying a group transformations. Okay? On top of this space here, this space here is has finite volume. It has a volume, invariant volume, and this volume is finite. But it's not compact, so it's not bounded. So you can go to infinity in this direction. And the way to go to infinity, when you have if you have, like I say, a sequence of lattices, you go to infinity if among this sequence of lattices you can find a subsequence such that the smallest vector goes close to 0. So the way you go to infinity in this space of lattices is when the smallest vector, non-zero vector, it becomes short. Okay. All right. So on that space, you can study flows. So flows are you look at SLDR. Inside SLDR, you have one-parameter subgroups, and these subgroups give you trajectories. So you can study the trajectory of lattices in that space. And what Margulis and Dani observed in the 70s and 80s is that there is a direct relation between the Diophantine exponent of a number, what we've talked about so far, and the speed of escape to infinity of a lattice associated to this number alpha. So here we are in the plane R2. We have this lattice delta alpha. It's the image of Z squared by a unipotent matrix 1 alpha 0 1. And you take then, so that's one lattice, it's associated to alpha, and then you take its image under this diagonal flow, e to the t, e to the minus t. So this will typically wrap around and become dense in the space of lattices. But how fast it can go into the cusp is connected to this Diophantine exponent in a very explicit manner using this formula gamma. So gamma here is the speed of escape to infinity, and it's beta minus 1 divided by beta plus 1. So you have one-to-one correspondence between this beta and this gamma. So how do you escape to infinity is the same thing as computing this Diophantine exponent. Okay. So yeah. So how people start to think about those things. So let me just open a small parenthesis. So this is Richard Margulis. The way Kleinberg and Margulis proved this conjecture of Mahler, this theorem of Prinzhuk, as I said, was by looking at the action of these flows on this space. And there is a particular lemma, a very important lemma, which was proven by Margulis in 1971, way before they had understood the connection between Diophantine approximation and dynamical systems. And this lemma appears in a rather obscure book published in 1975 at the height of the Cold War. It was a conference of proceedings in Hungary, of a symposium in Hungary, which was bringing together Western and Soviet mathematicians. And in this book, Margulis famously proves the well-known, the celebrated arithmeticity theorem, for which he won the Fields Medal some years afterwards. And this paper had something like 160 pages, huge paper, in which there is one lemma. And the lemma is crucial in the proof of the arithmeticity theorem for non-uniform lattices. But this lemma was so crucial that actually Margulis decided to put a separate paper out of it. So to devote to devote a separate paper. So there is next to this 150-page paper, you have a one-page paper containing the proof of this lemma. Okay, and this lemma is about showing that unipotent flows never escape to infinity. So a unipotent flow is a flow of the following form. So it's the matrix exponential of t times n, where n is a nilpotent matrix. Okay, so this is a particular type of flow on this space. And his lemma says that these flows never go to infinity. They always come back infinitely many often close to where you started with, okay, in a fixed bounded region. So this lemma was refined by Dani and gave quantitative estimate on the time spent in the cusp. They were used in a key way by Marina Ratner in the proof of her famous theorems on co-distribution of flows and homogeneous spaces. And they were instrumental. This lemma was key as well in the proof of the Mahler conjecture by Kleinbock and Margulis. So here's what Kleinbock and Margulis show. They show that they study a particular curve. So if you want the connection to the previous, what we were discussing before, so if you take this particular curve, u squared, u to the n, in Rn, and you start taking linear combination with integer coefficients, q0, qn, of this particular curve, then you just get the previous problem that we were talking about, p of alpha, p of u, where p is an integer, is a polynomial with integer coefficients. So their main theorem says that if you have an analytic curve or manifold in Rn plus 1, and if you assume that it's not degenerate in the sense that it's not contained in a proper subspace of Rn plus 1, then for almost every point on the manifold, the Diophantine exponent, which is defined in the same way as before here, is equal to n, and is also the minimum Diophantine exponent of any point on the manifold. So you again have the same pattern, that the Diophantine exponent of a random point on your manifold is the same as the Diophantine, as the worst possible Diophantine exponent. Okay, right? Okay, so so now I want to tell you about, how much time do I have, by the way? I don't know, I'm lost. 15 minutes. Yeah, that's good. So here is one theorem which is, as you see, is 18. So it's not yet even in preprint form, but here's a theorem, a new theorem, which we're proving with a former student of mine, Nicolas de Saxé. It is a generalization of both the Schmidt subspace theorem and the Kleinbock-Margulis theorem together. So it says the following: suppose you have an analytic submanifold M. Inside GLNR, so GLNR is a set of the group of invertible matrices. And then, as before, so you look at the rows of your matrix, L1, Ln, so you get linearly independent linear forms. And you ask, when is this product small? Well, the theorem says that, again, for almost every L, and every epsilon, then you can find a constant C such that this holds unless Q belongs to a finite number of exceptional subspaces. So it's completely, you understand so if your manifold is just one point, so then this is the Schmidt subspace theorem. So the point here is that there is an assumption that the Zariski closure, which is the smallest algebraic variety containing your analytic manifold, is defined over the algebraic numbers, over Q bar. So yeah, so if M is a point, you just get the Schmidt subspace theorem, and you also immediately recover the Klein-Bloch-Margulis theorem from it, just using one linear form. Yeah, and the others being just fixed. So, and here an important feature is that the exceptional rational subspaces that appear in the conclusion of the theorem do not depend on L, but they depend only on the Zariski closure. So they are not random. And they also do not depend on epsilon. And in fact, they depend on some additional geometric properties, geometric data associated to M. What they really depend on is just some rational Bourgeois varieties, which somehow govern how the manifold M it governs it's some more geometric data. So it could happen that M lies in some proper subvariety with the property that it always intersect. There are some special rational subspaces that always intersect the hyperplanes, the coordinate hyperplanes, and when this happens, then it will affect the exceptional. It will give some exceptional rational subspaces. So yeah. So the way we came up with, so I'll tell you in a moment how and why I started to think about those things. But here is, however, how we came up with this statement. So the reason is, I mean, the connection is really through this dynamical dictionary. So it turns out that it's possible to reformulate the Schmidt subspace theorem purely in dynamical terms. So yeah, and so the Schmidt subspace theorem in dynamical terms says that if you start with a lattice in Rn, which is spanned by vectors whose coordinates are algebraic, then when you take a diagonal flow, any diagonal flow, and so it means that you apply a diagonal matrix to it, then it will, some directions will be shrinked, some others will be expanded. And typically, if you take a typical matrix, then sometimes some directions will be shrinked, some others will be expanded, and at other times it will be the opposite. But here, if you start with an algebraic point on the space of lattices, then this flow will have the image of this lattice by this flow will have an asymptotic shape. So we'll have an asymptotic shape, and so this is it's a complete translation. So it doesn't it's not immediate, doesn't appear immediately that it's the same thing as the Schmidt subspace theorem, but this is a geometrical intuition. It's actually equivalent to the purely number theoretical statement I gave you before. Okay, so right. So let me now in the last maybe 5 or 10 minutes, I don't know, tell you briefly how I came to think about these problems. So I came to think about these problems because of some conjecture of Peter Sarnak here. Here's Peter Sarnak. He conjectured some very simple, fundamental fact, or it's still conjecture, about rotations. He conjectured that if you take two rotations of the sphere of R3 at random, okay, so you take an axis at random and you take an angle at random. If you take two such things at random and you start taking products of these rotations, you have A and B, you take A, B, A, B, A, B squared, A, and so on. Take all products of length n. Then, well, it should be that after time n, if you look at all words of length n in A and B, then it should be that it ought to be the case that this set of rotations that you get, typically you're going to get maybe 2 to the n rotations like that, then they should be equidistributed. They should be very well equidistributed in the group of rotations. So on the sphere, you should be able to cover the sphere so these 2 to the n points look like they are equidistributed on the sphere. And so it's known that they are equidistributed, but the question, the conjecture is whether it becomes equidistributed with an exponential speed. And this is called the spectral gap conjecture, spectral gap problem. And it was known for a while. So this is a formalization of what I just said, showing that you have a spectral gap or showing that you have exponential speed of convergence of these products of length n is the same as showing that a certain operator has norm less than 1 in L2. So it's a very difficult question. In fact, the only examples of A and B or GIs here of specific matrices for which we know that there is a spectral gap come from solutions to the very difficult problems in the Langlands program, in particular the theorems of Deligne and on the Ramanujan-Peterson conjectures. So it's surprising, but because it ought to be the case that for a random A and B it should be true, not just for a very specific A and B. So all right, what's the connection to the Diophantine approximation problem? Well, it was realized for a while, and it was proven completely by Bourgain-Gambaud and Benoit and de Saxé that this spectral gap property is equivalent, or at least is implied, but in fact equivalent, to the property of the group to be Diophantine. So I say that a Lie group, like the group of rotations, SO3, is Diophantine if, when you take words, you take A and B at random in the group and take words of length n, then these words never come too close to the identity. Okay? And too close is measured again by a Diophantine exponent beta here. In the case when G is the real line, just the real line with a plus, additive real line, you recover the original definitions I've given at the beginning of the talk. So it's really one and of the same thing. Okay? So this is non-commutative version of the same problem. Okay, so the connection is this theorem that if G is Diophantine, meaning that words of length n can never get too close to the identity, then you have a spectral gap, and therefore you can. This means that the random walks equidistribute with a speed with an exponential speed. All right, so we can't prove this property. So that's already a huge mileage because you go from spectral gap to Diophantine. But there's still an open problem nowadays to show that the group of rotations O3 of R is Diophantine, has this property. However, that we don't know. I'm just going to tell you one last thing and stop. So it might be, you may think that every Lie group is Diophantine, but that's not true. So we found some example of nilpotent groups of class 6 that are not Diophantine, even though all nilpotent groups of class 5 or less are. And but finally, using this Schmidt subspace theorem for this random Schmidt subspace theorem for manifolds that I told you about with de Sachet, we managed to, the only thing we managed to do so far, so that's still work in progress, is to compute this Diophantine exponent in the case of a large class of groups, nilpotent groups. But this, of course, does not include compact Lie groups like SO3 or SU2. So that's all I wanted to tell you today.
Thank you very much for the very nice talk. I apologize for people who come later. We have some technical niche, and we apologize we have a bit of delay in the program. I think we have some time for question or two. Yes.
You have a extension of two theorems that you showed before, and in that theorem also a C shows up. It does not depend on epsilon, but can you say something sensible about that C
No.
compared to the other ones?
Yeah. So this C, no, it's in the random case. This one here, maybe.
Yeah.
This C here will depend on the particular random point in M that you find as well. So you can't say. Yeah.
Yeah, just a small question. In your case, the homogeneous flow without relation with the previous topic, is that for compact simple group? Can you work with other groups like
right.
semi-simple?
Yeah. So for the what makes things work in the nilpotent case is basically a linearization procedure. The nilpotent groups are not too far off from being abelian, and so you can think of words in nilpotent groups, words, as a lattice in a bigger nilpotent group. And then you can do homogeneous, you can look at this quotient as a homogeneous space. But in the semi-simple or simple semi-simple world like SO3 or SL2R, then that's not true anymore. So it's a complete different business. Yeah.
Thank you.
Yeah.
We'll start. Yeah, we will start at 3:30. 3:30, yeah. And tea and coffee is there. Let's thank the speaker again.